Okay, there are two types of ionic reactions. One is called single replacement, the other is called double replacement. I'm going to cover double first because most people get that one better than the other one. Might as well cover the easy one, not easy, but more a more clear process than the other one. Okay. Now I do things differently because I'm in charge of the class. So about 20 years ago, I decided that going by solubility rules were a pain. Most teachers make you memorize them. I don't. And so to make things more visual, because a lot of learners are visual learners, I made a black and white table. So you don't have, and it's based on the rules. So the rules are right here. And they're kind of a pain. Kind of a pain. So, I saw my students struggling, up in Washington. I decided to make that there. And I've changed it quite a bit, but most people understand it. Now, basically, a double replacement reaction we were talking about today involves two salts being mixed together. And the two salts are not soluble. I mean, they're soluble, so there's no solid in there. So it looks like plain water, plain water. Dump them together, and something may or may not happen. This will tell you whether something happens or not. So you look at the main constituents, and I'm going to give you lots of examples. So let's look at okay, sodium chloride. It's got sodium ions, chloride ions, silver nitrate. It's got silver and nitrate ions. So salt, because it's ions, salt, ions. Now, single replacement, there's one salt and one metal. So that's the difference between the two. Salt, salt, double replacement, salt, metal, single replacement. And that's tomorrow. Okay, so what we're going to pour these together. Now, the sodium chloride in the beaker, nothing's happening. It's just clear. Same with the silver nitrate. When we put them together, though, we've got a new combination available. That combination is the sodium and the nitrate can kind of be a salt, and the silver and the chloride could be a salt. Okay, so let's take the top one first, sodium nitrate. This is how to use this table. You find sodium on here, it's right here, and nitrate, which is right here. Okay, notice where they merge together. Right here, it is white. That means nothing happens. So the sodium is still sodium ion. Nitrate is still NO3 nitrate ion, not hooked up to anything. Okay, so let's do the other one now, okay, which is chloride. And silver. Okay, so where the chloride comes across, and where the silver comes down, this intersection is black. that means something's going to happen. Usually a precipitate or a solid forms. So when we mix these two together, and in this new concoction, this becomes a solid. And this becomes separate ions. That's called AQ. And these are going to be over here, AQ as well. Meaning they're just plain old ions. Now, this is the deal with solubility. It's kind of a cool concept. When we have beaker, we throw some salt in there. What happens is, and we mix it up, it all dissolves, no leftovers. What happens is these come apart. Okay, so if we were to look at this with a horrendously good microscope, we would have a crystal of salt. And it's called an ionic solid because it's held together with opposite charges. Okay, now, then we have, this is surrounded by water. Now, water looks like this. And water is a very powerful polar solvent. That means at one end, it's sort of negative, and the other end, it's sort of positive. So now you got all these water molecules running around with positives and negatives. Now, those are partially negative and partially positive, not totally negative. Okay, so what happens at the surface of this ionic solid, you have the sodium, you have the sodium ions on the surface, chloride ions on the surface. Now, motion is always going on except at absolute zero. That's minus 273 Celsius, really cold. Other than that, everything moves. And there are 5 modalities of movement. One is just going from here to there. Another is rotating. Another is doing this. Another is, going like all these different movements happens except at absolute zero. So this guy is always bumping into that crystal. The higher the temperature, the more it bumps. That's why when you dissolve your sugar in your coffee, it dissolves easier in hot coffee than cold coffee. Because in hot coffee, they're moving more. So statistically, the chances of this hitting the surface of that salt crystal is higher. Now, what happens is this negative oxygen, remember partially negative, attracts that positive sodium and it pulls it out of the crystal. Over here, we have those positive hydrogens working on the negative chloride. So after a while, the crystal solid, the ionic solid is no longer a solid. It's pulled out by the water. And it's because the water is very polar. Now, if we threw in there something like gasoline, which is not polar at all, the salt would stay crystal because there's nothing that's going to attract those sodium and chloride crystals or ions. Okay. So that's why on the black chart, the sodium chloride here is white. Now let's look at this diagram some more. Okay, so we have a beaker full of sand, and filled with water. Okay. Why does the sand not dissolve? Got oxygen in there, polar, doesn't dissolve though. So you've got a fundamental two forces battling it out at the microscopic thermodynamic layer. You've got crystal lattice force that keeps the crystal together. That's one force. And the other one is the solvating force. And the solvating force pulls the crystal apart. So the question is, which is stronger? Let's look at sand again. Which is stronger in the case of sand and water? The solvating force or the crystal lattice force?
The crystal lattice force, since it's together.
No, it's staying together. What force keeps things together?
The crystal lattice.
Force. So in the case of sand in water, the solvating force is weaker than the crystal lattice force. Hence, it's staying in one piece. Now, in the case of salt in water, which is stronger, solvating or crystal lattice force? Solvating, because it's pulling it apart. So those are the two forces battling it out when you have a cup of coffee. Or just plain water with salt in it, plain water with sand in it. Now, one of these is affected by heat, temperature, and the other is not. Solvating, temperature affects it. It makes it more effective. So the higher the temperature, the more effective the solvating force becomes. So you may put something in water, cold water, and stir all day and nothing happens. You warm it up, it dissolves. That's because the solvating force is directly related to temperature. Higher the temperature, stronger the force. Crystal lattice force, not temperature affected at all. Okay, so does that make sense on this? How does something dissolve? It's at the microscopic atomic level. Okay. Now this thing here, we're going to do tomorrow. That's for single replacement reactions. Okay, so does everyone understand? These are the rules, by the way, we use to create this table. And normally a teacher would say, know them. And then August 1st, you'll have forgotten about them.
Well, I had a
This
quick thing.
table, you can use the rest of your life. Very easy to understand. I've never had one person say, I don't understand this table. And if you're, I used to teach a prep class up at Sierra, and that was a prep class for going into 400, which is their 1A up there. So then I had to teach them the rules because their 1A teacher wants all the students to know the rules. Then I said, I'm going to give you both, but this is what you're going to have to learn when you get to 1A or actually 2A. Every teacher up there makes you memorize a whole bunch of stuff. You know, that common ion chart I gave you? They expect you to memorize that. I'm sorry. Pedagogically, that's not sound from my perspective, particularly if you're equipped with a smartphone. I'm old too. I have old ideas and stuff, yet I think a smartphone is really a good deal for students. But a lot of teachers don't think that way. They go, it's ruining our education system. In fact, California just recently passed a law about that.
Because then school can't have them.
Oh,
They're
to
trying to pass that.
either limit it or not at all,
They're making them when they come in. the classroom.
in a box or something like that, yeah.
And mix it back from like, well, what if I do?
Yeah. Or there's an emergency, you know, I mean. Okay, so, now. Let's do this. Okay, so there's a lot of parts to this. One, you need to figure out whether the new combination is going to be soluble or insoluble. Insoluble means it forms a solid. Now, your lab next week, everyone loves the single and double replacement labs. They're very colorful. You're gonna put stuff together and colors change, or you get bubbles form and stuff, and you can predict it. They're pretty cool labs. Up at Sierra, that was the #1 lab students really liked. So this is the underlying theory behind it all. Okay, so let's look at this reaction we just did. So we have sodium chloride, AQ. That means it's dissolved in the solution. Same with the silver nitrate. Now, the new combination is basically we're going to swap out the cations, or you can swap out the anions. It doesn't matter which one. So the new combination is going to be silver chloride plus sodium nitrate. Now we just found that the sodium or this silver chloride is a black box, so that means it's a solid. And we found the sodium nitrate was a white box, meaning it's soluble. So that's an AQ. Okay, and make sure it's balanced. And I purposely chose ones that don't need to balance it because they're all plus ones and minus ones. So it's already balanced. But you need to check that though, just to make sure. Okay, so this is called the molecular equation. Now, there's another equation called the total ionic equation, which means you take everything apart and it becomes a detail-oriented activity. We're not going to do that in this class. We're going to go from molecular. Now, the last equation it's called the net ionic equation. Okay, what that means is, did something happen when we put the two solutions together? Yes. We had we had silver chloride form a white precipitate or a white solid. So the net, what does the word net mean? Like, can you say net it up? Huh? Yeah, just get rid of the superfluous stuff, right? Just tell me what's going on. Okay, so a net ionic equation says what's going on. Sometimes nothing happens when you mix them together. So that would be, oops, a null set. Okay, if something happens, okay, so we made silver chloride solid. What did we make it with? What else? Because silver chloride doesn't just appear out of water. How do we make it? There's two parts, right? What are the two parts? Silver and chloride. So this is the net ionic equation. Now, if you get no solids forming, then it's null set. And lastly, one more part here is spectator ions. Now, when I go to the game next week, am I a player or a spectator? I'm a spectator. I don't go out in the field and throw the ball around and bat and all that stuff. So do I do anything for that game? Not a bit. So spectator ions do nothing. So spectator ions here are sodium and nitrate. So for each reaction, double replacement reaction, you're gonna have the total molecular equation. You're gonna have a net ionic equation and spectator ions. Okay. All right, so let's do another example. Oh, let's see now. Yeah.
So the spectator ions, those are just the elements that had no reaction.
They're just there. Just like me at the baseball game, eating hot dogs, drinking beer. Assuming I can go. I went to I should say I bought tickets for Flamingo Spanish restaurant in Sacramento. It's called Top of the World. Anyone eating there?
In Las Vegas?
Here, Sacramento. It's on J or L, Midtown. Great place. Well, twice or three times a year, they have flamingo dancing. From San Francisco come and perform. And it's a catered dinner and it's like $130. And my dinner group, we all decided to go. I got sicker than a dog that day, but I gave my ticket to someone else for it. $130. So that's this Friday. There's no way I can just take it away.
What is flamingo dance?
It's very cool.
They dance like a leg with.
No, it's a very intimate dance. Now, I didn't tango, only it's not. Look it up, it's pretty cool.
Yeah.
And they have
On top of the.
I play the guitar and piano. The guitarist there, he's playing this flamingo. Unreal. I mean, that's.
Like some Carlos Santana part?
Yeah. It's very different, I think.
I mean, it's,
I saw him live
yeah,
on I used to run a lot when I was younger, and I did the Bay of Breakers and Holyfield at the end of 17. First time I ran it, I was really cool. And I listened to him from Woodstock, and but I wasn't a fan, so I saw him live.
yeah.
Yeah. Basically, what are you starting with? Starting with the two solutions, right? So what's in one solution? What's in the other solution? That build on the ladder. Mix them together. The cation exchange, you have a new combination. And then we look at it on the table. Is it a black box or a white box? That's what it's.
That's once you switch it.
Huh?
That's after you switch it. Like after you switch the same thing.
Yeah, so then after you switch is on the product side. Before you switch is on the reactant side. Reactant side, no way.
Well, that's the switch.
Yeah.
You can just switch the cation performance. Or you just swap the.
I think let's use the swallow first for the
They
second.
just have to have new parts. Now, a friend of mine, he teaches chemistry when I taught high school for a couple of years up in Washington. And he was in the lab next to me, and we became really good friends. So the way he teaches double replacement reactions. He goes, you and your girlfriend goes to a dance, and you meet up with your good buddies, girlfriend and him. Everyone has a fight. What happens? Swap partners. And go home. And he has a single replacement version of that too. I don't like these encouraging antisocial behavior. Anyway, he was very good. He had more stories than I have, which is saying a lot. He, big giant guy. He, redhead, big giant guy, he was like 6'4", 6'5". Used to, really into, lifting weights and everything. Yeah, his lift weights so big, he tore his muscle off his bone. That's. Yeah, I know, called narcissism. Like, he was a good guy. He and I became really good friends. Okay, so let's do another one.
After a little bit, he like.
Yeah.
So this.
Yeah. Yeah, you can have a number of, you can have a, periodic table, that chart, in fact, you're gonna have the chart I had up there, this chart. Which includes this on the right, yeah. Cause you need that for a single replacement. You have a common iron chart, I mean, a common iron list as well. Yeah.
Double like.
Oh. Because I'm like. You don't make. No, they're not done. It's like somebody iterate, like this, what really. There's a lot in there, yes. Translating.
Okay. All right, barium chloride. Barium chloride and lead nitrate. I looked on the chart and these combinations are all white. Okay, so I'm starting the molecular equation. They always do that first.
What's that say, two, eight,
Huh?
what's that, outside the two?
AQ or aqueous.
You just a little bit, eight.
Huh?
You
Make it bigger?
Yeah.
The only problem, I have to extend this though for the product side. Let me write that and I'll make it as big as possible. Okay, so swapping out the cations. We end up with this new combination. Lead chloride. With barium nitrate. Well, first of all, this is not balanced. We need to balance it. Okay, so it's balanced now. So, new combination is lead chloride, black or white? Lead chloride,
Is chlorine
lead, PB.
lead?
No. Oh, excuse me. Let's go up here. Okay, so here's lead at the top. Boom. Here's chloride on the left. So, black. So that means lead chloride needs an S by it for solid. And then the other one was a nitrate, barium nitrate. So nitrate's at the top, barium's here. So the barium nitrate is white. Now, sometimes you get two blacks or two whites or a combination. It just depends what you're dumping together and whether the solvating or crystal lattice force is stronger with one or the other. Okay, so this is going to be a solid. And that's an aqueous. Yeah.
Atoms adding up to and out three about.
I didn't write. Well, that's what happened. Okay, so that's our molecular equation. Sometimes abbreviated ME. I like to write it out, but sometimes you'll see ME. So did something happen when I dumped these two together? What happened? Solid. So that means we have a net ionic equation now. So lead chloride was a solid. So what do we put together to make that? Lead. Now, lead positive 2 is on the top. It'll tell you what charge it is. The negative charges are on the left. It'll tell you what charges are there. Okay, and then how many chlorides made that lead chloride? 2. So this is our net ionic. And then what are our spectator ions? Well, barium didn't do anything. And the nitrate didn't do anything again. So this guy, that, this guy is that. In the total ionic equation, you can look it up if you want. It gets very detail oriented. I mean, extremely so. And you lose track of what's going on really because of all the little details. I mean, I'm not exaggerating here. Okay, so does that make sense? Yeah.
So on the test, if we get a reaction, you want us to write out also the net equation as well as the spectator.
Yeah, if nothing happens, you still need to put a null set. Yeah.
Oh, yes. Okay.
There's the 0 to the 1.
Yeah.
Or write it out. I mean, it doesn't matter. I usually do null set. But you can write it out. I'll just say no reaction happened, something like that. All right, is this making sense? Okay. Now you're going to actually see this happening. With droppers on micro scale. And some of the solids are white and some are different colors. Now, in my labs up in Washington, we did something called qualitative analysis. I gave you an unknown and I said, what's in it? So you had to go through all these wet tests for the flow chart to determine what it is, what's in there. For example, a mercury, lead, silver test is with sodium chloride. You drop in sodium chloride in white solid forms, you know you have one of those metals in there. That's an example of one of the wet tests you do. So you have this flow chart, and you go through, we called it quants, or qualitative analysis. And it took a whole, now we were in the quarter system up there, so it took a whole 5 weeks to do this. And it was, to me, it was, the students really liked it, but to me, it was an awful lot of time spent on that. Okay, anyway, sometimes labs will have that built in, sometimes they won't. Okay, so that's it for double replacement reactions. And tomorrow I want to cover single replacement reactions.
Yeah, that's the first. So the first thing you do is to kind of combine them, the cations and anions of the two sides. That's the first step. And then the second step is to balance the equation
Yeah.
of that thing you just wrote,
But
and then add them together.
So that's the first, that's the molecular equation. And then we need to check the status on the product. Are they solid or aqueous? That's what the table, black table. Misty, can you read that? Small,
it's small, it is
and you're not wearing glasses.
slippy.
So does that try to make sense?
Oh, the net ionic equation. What was that again? What was the
If something happens,
Yeah,
how did you make it? Like in this case, we made lead chloride. Okay, that means we have the lead ion and chloride ion coming together to make the lead chloride solid. Okay, don't forget to view the video.